So welcome to part 3 of solving linear simultaneous equations, and this is visualizing the problem. Now, a colleague and friend once said to me, trying to see the problem clearly is clearly the problem. And what he meant by that is that if you don't define the problem clearly and correctly at the beginning, then you'll find it very difficult to solve that problem and you may get it wrong. And one way to look at the problem is through visualizations, and that's what I intend to do here. So let's have a quick summary of what we've already done. We know that we can either have 0, 1 or infinity exact solutions to ax equals b. And if there are 0 exact solutions, then we must either have 1 or infinity least squares solutions. We can look at every possible occasion and find the solution via the pseudo-inverse, which we obtain through singular value decomposition. So here's an example where we have 0 solutions, but we have one unique least square solution. Again, 0 solutions, but infinity of least square solutions. One unique solution to ax equals b, an infinity of solutions to ax equals b. By the way, as I say, these figures are just illustrative. That means there's many different ways in which these situations can arise, and we'll now look at those visually. So continuing with this summary, for ax equals b, the matrix A can either be square, tall or fat. The set of equations can be consistent or inconsistent. And the matrix A can be full rank or rank deficient. So that's 2 times 2 times 3, which gives you 12 possibilities. But in fact, only 10 can exist, as we're now going to see. So here I've summarized all the 10 possibilities. This case where A is square, inconsistent, and A is full rank, can't happen. Where A is where A is fat and inconsistent, can't happen. With a little thought, you should be able to understand why that's the case. But anyway, let's go through it. And for each case, I'll look at the case of consistent or inconsistent. So here's a set of equations which are consistent. So in this particular case, we know that the augmented matrix rank AB equals rank A, and we look at the case where rank A is full rank. Okay, so there's 2 examples I've just given. This is 2 unknowns, this is 3 unknowns. This is what you would get. Here the 3 planes cut at exactly 1 point. Here's the case where A is not full rank, and so what you get there is you get an infinity of solutions. Here's a case where there are 2 lines, that 2 black lines, one on top of the other, and the red line shows the solution. There's an infinity of solutions. Now let's look at the case when A is square and ax equals b is inconsistent. So when it's inconsistent, we mean ax is approximately equal to b. So let's look at the case when A is not full rank. So when A is not full rank, there is no solution, but there's going to be an infinity of least square solutions. There's no solution but an infinity, the red line, of least square solutions. And here we have 3 planes, and there's no solution but there's an infinity of least square solution. So you can see the case where A is full rank, when A is full rank, does not exist. So you can't have A square, ax equals b inconsistent, and A full rank. And I've done similar visualizations for the case when A is tall and when A is fat or underdetermined. Okay, so let's look now at some examples. Here I have 3 equations and 2 unknowns. And if you look at the rank of the augmented matrix and the rank of A, they are different, which means that the equations are inconsistent, which we can see here. There's no unique solution. And if we also look at the rank of A, the rank of A is 2, and that means it's full rank because it's equal to the minimum dimension, 3 by 2, so the minimum dimension is 2, so it's full rank. So if it's full rank, that means there's a unique least square solution. So this tells you that the equations are inconsistent, and this tells you that the rank is full rank, so there's a unique least square solution, so you get this. Now here's 3 equations and 3 unknowns. And again, the equations are inconsistent. so there's no unique solution. But if we look at the rank of A, it's equal to 2. Maximum rank would be 3, so it's rank deficient. So that means there's not a unique least square solution, there's an infinity of least square solutions. And in this case, the rank of the augmented matrix and the rank of A are both equal to 3, so it means it's consistent. And since this is full rank, it means there's a unique least squares solution. So those are just 3 examples summarizing what we've already learned. Okay, so now we're going to look at how we visualize the problem in 4 different ways. So we start with AX equals B. By the way, 2 of these ways we've already seen. So we're going to consider a least squares solution to an overdetermined system of equations. So if you take AX equals B, you can visualize that, in this case, as being 3 equations. And those 3 equations can be drawn like this. And we have here, in this particular example, a unique least squares solution. Okay, that's the first visualization. Now let's have a look at the second visualization. Let's look now at a second visualization. So the same set of equations. We know in general that B will not be equal to the left-hand side for an overdetermined set of equations. And so we can say that B is not equal to x1 times a1, this column vector, plus x2 times a2. Now what do we mean by that visually? The 2 columns a1 and a2 will span a 2-dimensional plane in general unless they're collinear. And B, which is a 3 by 1 vector, the chances that it lies in that plane are very unlikely. And so we cannot say that the left-hand side and the right-hand side will be equal, because B cannot be spanned by weighted values of A1 and A2. And what we try to do is we try to choose X in such a way that the projection of B onto that plane, that distance from B to the plane, is minimized. We're going to see that later. Okay, now we have visualization 3. So the same set of equations. Now what we're doing here is we're producing a point in 3-dimensional space. So we choose 3 axes alpha, beta and gamma. And then we take a point A11, A12 and B1 and we plot it here. We get another point with the second row and we plot it here. And we get a third point and we plot it here. And that's the origin. So we consider this plane is x1 alpha plus x2 beta equals gamma. So these are the 3 variables, gamma, beta and alpha, and x1 and x2 are the coefficients of alpha and beta that we're trying to estimate. Now what's the criteria for, or criterion for estimating x1 and x2? Well, we want to make the left-hand side equal to the right-hand side. So for example, we know it must go through, that plane must go through the origin, because when alpha equals beta equals gamma equals 0, it'll go through that origin. Now what we'd like to do is to sort of keeping the plane going through that point is adjust the plane upwards, downwards, or twist it such that it now picks up that point. So if it picks up that point, you're going to get x1 a11 plus x2 a12 equals b1, which of course is just the first equation. a11 x1 plus a12 x2 equals b1. So if the left-hand side was equal to the right-hand side, that would manage to go through that point. Now we have enough degrees of freedom to swivel it around and pick up that point. We have 1 degree of freedom left, and we can move it again, think about it, to pick up that point. And that will give us the second equation. But we don't have enough degrees of freedom to pick up this third point, unless fortuitously it just happens to lie on that plane. And so what we have to do is, constraining the plane to go through that point, we have to adjust it so it's as close as possible to all of the 3 points. So that's a different way to look at how we solve this in a least squares sense. Okay, here's visualization 4. So if we take the objective function that we're trying to minimize, and we write it like this. Don't forget, we put in, for vector x, we put in x1, x2. So what we've got here is a quadratic in two variables, x1, x2. So we can plot this, and it looks like this. Now, if this set of equations is consistent, then the bottom of the quadratic will touch the x1, x2 axis, and the objective function will go to 0. But in general, this will not go to 0, and so we have to get a least squares solution, which is the bottom, the x1 and x2 corresponding to this point, the bottom of that 2D quadratic. So as an example, if we take that's the value for A and that's the value for B, we end up getting this expression for the quadratic in two variables, and we know what that's the least squares solution. So we get 0.4038, 0.5038, and it corresponds to this red point here. And the minimum of that quadratic can easily be shown to be this, which is 0.3967. So that's the fourth way of visualizing the problem. Okay, if we continue with visualization 4 and we just go a little bit further, if we take this A transpose A, which is now a square matrix, and we look at its eigenvalues. So if you don't know what an eigenvalue is, just look it up. It's quite simple. It's just multiply it by a vector V, and if all you do by pre-multiplying it by A transpose A is just change the length, so you're not changing the orientation, you're still getting V back again, or V sub I, and all you're doing is changing it by the length, that becomes an eigenvector, and that becomes an eigenvalue. Now if you plot the maximum eigenvalue over the minimum eigenvalue, and you get, say, 10, then it will look like this. As this ratio goes up, it becomes more stretched. The ellipse part at the top here, the major and minor axes become, major becomes bigger and the minor becomes smaller. And then when you eventually get a spread of infinity, this is what happens. So this is the case where in these two cases you've got two uniquely square solutions, and when the maximum eigenvalue over the minimum eigenvalue goes to infinity, you get this. So that's a way of visualizing what happens to that surface when you have an infinity of least squares solutions. It becomes like a bit of guttering on a house. So let's have a look at this interesting visualization. It's a visualization to find the least square solution. It's via what's called the orthogonality principle. So we want to minimize this objective function, and we want to find x as xls, the least square solution. Now we know that we can write ax like this, x1 times a1 plus x2 times a2, where a1 and a2 are the two columns in A. So we know that ax, or in this case ax least squares, must lie in the column span of A. So it must lie in this blue plane, because this will access any point in that blue plane. Now we can clearly see that in order to minimize the length of E, we must choose the green vector such that E lies perpendicular to this plane. So now consider when E is orthogonal to this plane, it must be orthogonal to any vector in that plane. So how do we find any vector in that plane? Because this is not any vector, this is the fixed vector xls. This is the solution that we're looking for. So if we choose P as a 2 by 1 vector and A is a 3 by 2 matrix, so A times P will give us any point on that plane, or will give us any vector on that plane. So E must be orthogonal to AP. And if E is orthogonal to AP, we can say that the inner product between E and AP must be 0. Find the inner product by taking the transpose of E, multiplying it into AP. Since this is a scalar, this product is a scalar, we can take the transpose of both sides. We take the transpose of both sides, and then we replace E by B minus A XLS. Where did I get that from? Because E is equal to B, that's B, minus, going in that direction, XALS. And that must be equal to 0. Now here's the clever bit. A transpose B minus A XLS is a fixed vector because XLS is fixed. But P is a 2 by 1 vector, and it's any 2 by 1 vector. So what we're saying is that the inner product between any 2 by 1 vector and a fixed vector is 0. The only way that can happen is if the fixed vector is itself 0. And so when we just rearrange that, we end up getting the familiar least squares solution. So a second way of visualizing the least squares solution is to do what's called look at projection matrices. Now, what we can look at here is projecting B onto the blue surface, which is in the column span of A. And it's well known that if you want to project a vector onto a surface, then you pre-multiply that vector by the projection matrix. And the projection matrix is given by that formula where the columns of A span the surface on which you wish to project. So what we can say is that projecting B onto that surface should give us ALS. And all we do is simply substitute for the projection matrix and then a bit of rearranging, pre-multiplying, and you get the familiar solution. Third way of visualizing the least squares solution is to look at the concept of null space. So we've got the error vector E, and it must be orthogonal to this blue plane, which means it must be orthogonal to any vector in that blue plane. And we know that the two column vectors of A lie in that blue plane, so E must be orthogonal to A1 and A2, which means the inner products must be 0. So if I write the inner products, two inner products as 0, I get that. If I rearrange, I get this. I take the transpose, both sides, and I get this. Now I substitute for E, and E is equal to B minus AX LS. So I do the substitution, I get this, and then I rearrange. And I get that familiar solution again. So just comment here that E must always lie in the null space of A transpose. That's what that result says. And in fact, it's nothing to do with least squares. It just simply says that if you have a plane, and that plane is spanned by the columns of the matrix A, then any vector that's orthogonal to that plane will lie in the null space of A transpose. The null space of a matrix are all the vectors that when you pre-multiply by that matrix you get 0. So now we've finished section 3, let's go on to section 4. And section 4 is looking at how we solve AX equals B, where instead of looking at the least squares, the sum of all the squared error terms, what we look is at the sum of the squared error terms, but where each error term is weighted differently. So we give different emphasis to each of the particular errors. And we'll also look at the idea of introducing constraints. So we want to minimize the norm AX minus B squared, but we have certain constraints on the solution X. So there's two aspects which are extremely important, and I'll see you in section 4.